This is Edexcel Further Maths, Further Pure 1 Specimen Paper, question 4. We've got a question here involving the modulus function and a quadratic. And we're asked to find the complete set of values of x for which this holds true. Now, the first thing to notice when you're dealing with a modulus function problem, particularly if you need to solve equations involving this, is that the modulus of a function, whatever the function is always equal to either the function itself, provided the function is non-negative, or it'll be equal to the negative of the function, and that happens when the function gives a negative value itself. In other words, if your function is churning out a negative, then the modulus function will change its sign. But if the function is giving you a positive value, it does nothing to it. So it either changes the sign because the original thing was negative, or it doesn't change it because the original thing was positive. Now that means that we need to investigate two different possibilities. We need to consider the curves y equals mod x squared minus 2 by considering y equals x squared minus 2 and y equals minus x squared minus 2. In other words, minus x squared plus 2. Now, we should be able to sketch those fairly easily, and I would highly recommend you incorporate a sketch into your repertoire for a question like this. So we'll start with what we know about this basic quadratic. It doesn't matter if your curve is not particularly beautiful. It doesn't need to be a work of art. It just needs to be sufficiently clear that you can use it. So if this is our quadratic, we can indicate straight away some things that we know. Crosses the y-axis at 2. I'm considering this one to start with. And the x-axis at root 2 and negative root 2. So we can incorporate that into our diagram so that we can see more clearly what's going on. In fact, it crosses the y-axis at negative 2, this particular one. But what we're going to do is develop the modulus function graph, which does cross at 2, as we'll see when we start reflecting it. So I'm going to leave that 2 there. The root 2 and the minus root 2 we can fill in there. This is what happens if you try solving x squared minus 2 equals 0. Or in fact, if you try solving the negative of x squared minus 2 equals 0. We're going to cross the y-axis at 2 because when we take the modulus of this function, we get the same curve for most of the time, except when our curve goes negative, the modulus function curve breaks from it and starts showing us the mirror image, effectively. Now you can even imagine the negative quadratic where it could have gone down there. And in fact, it might be a good idea to make this a dotted line to show that actually our curve is just this one that's strictly above the axis. If we include that, then we've got a pretty clear idea of what our graph is doing, and we can use it to solve the problem that we're given. Now, in addition to that, we can sketch y equals 2x. We should put that on the same set of axes so we can see more clearly what we're trying to solve for. So use the fact that when x equals root 2, 2x will be 2 root 2, which is about 2.8. So we're already going to be a little bit higher than the 0.2 on there. In fact, this curve and this line together should look something like this. Again, it's not particularly crucial how you do it, but remember, a quadratic will always eventually beat a straight line. So in the long run, we're always going to be in a situation where the slope of the quadratic overtakes the slope of the line. we're going to have a point here where they cross, a point here where they cross, and a couple of what I call phantom solutions, points where the line might cross a quadratic, but the quadratic isn't necessarily part of the modulus function curve, because it's a bit of the curve that the modulus function doesn't emulate. The modulus function is the same as the positive quadratic whenever x is not between root 2 and minus root 2, and it resembles the negative quadratic whenever x is between root 2 and minus root 2. So we need to make use of that idea. Include this diagram. Now they've said to use algebra to find the complete set of values. We also need to make sure we give our answers in set notation. We'll worry about that when we come to it. In order to solve this then, we're going to need to look separately at either x squared minus 2 equals 2x, and then at negative x squared minus 2 equals 2x. So let's take this one to start with. This is the positive x squared. We can rearrange it into the standard format, and then we can jump to the calculator and use the calculator's solving mode for polynomials of degree 2. So we have a 1x squared, we have a minus 2x, we have a minus 2. Yeah, that gives 1 plus or minus root 3. So we've got two possible values. 1 minus root 3 is not in the range. In particular, if you do 1 minus root 3 and you square it, and then you take away 2, you should notice that the answer is less than 0. So it can't possibly be a valid point here, because you can't, if we have a value for x that makes this negative, then x squared minus 2 can't be the same as the modulus of x squared minus 2. We're looking at the first case, might even call it case 1. This is where x squared minus 2 has to be at least as big as 0. We're considering where my line crosses the positive quadratic. And so you can see we've picked out one of the phantom solutions. That was 1 minus root 3. But on the right-hand side, the positive, or the larger of the two solutions in this case, is the solution that we care about. That's the one that actually tells us what x could be. So we get x is 1 plus root 3. For case 2, we have x squared minus 2 has to be less than 0. This is the situation where the sign would be changed by the modulus sign. So we get the negative of x squared minus 2 is equal to 2x. When we rearrange that, we get minus x squared minus 2x plus 2 equals 0. Again, we can use the quadratic solver on the calculator for this. We have a minus 1x squared, a minus 2x, and a plus 2 at the end. This gives us minus 1 plus and minus 3. So again, we've got two solutions. Minus 1 plus minus root 3, should I say. And this time, as before, we've got a phantom solution. The phantom solution is minus 1 minus root 3. This is where I'd say it's much easier if you've got the diagram already, although what we're stating is all purely algebraic reasoning, you might think. I'm using the diagram to help me and to check that my answers are coming out as they should. I can check, for instance, that 1 plus root 3 is in fact bigger than root 2. 1 plus root 3 is about 2.7, root 2 is about 1.4, so it fits. And 1 minus root 3 is less than root 2. In fact, quite a bit less. 1 minus root 3 is going to be minus 0.7 something. So that being down here, below root 2, but not as low as minus root 2, is consistent with my diagram. I can say here that minus 1 minus root 3 is not in the range. This must be the very furthest to the left of our phantom solutions. We can justify it by saying that if you square minus 1 minus root 3, you take away 2, you get an answer that's bigger than 0 instead of less than 0. So that's the algebraic justification for rejecting that solution. And that leaves us with the other one, x is minus 1 plus root 3. Now, so far, all we found are the critical values, but that's the hardest job done. We've worked out where the two cross, and because we've still got a graph, it should be pretty easy to infer the final parts. We just need to know when the modulus function, the curve, is above the straight line y equals 2x. And that happens at a couple of regions. It happens if x gets big enough, because then you'll be squaring something big. And it happens if x gets low enough. In fact, anything below this point here, the quadratic modulus curve will be higher. And anything above this point here, the quadratic modulus curve will be higher again. So there's no single region that works, but there are actually two disjoint regions. And that might be the reason they've asked for the set notation as well, because set notation is a logical way of describing two disjoint regions like this. Without set notation, you might write something like x has to be greater than 1 plus root 3, or x has to be less than minus 1 plus root 3. With set notation, we put these curly braces around, and we say we want the set of all values x such that x is greater than 1 plus root 3. And then we say I want the union of that set with this other set, the set of all values x such that x is less than minus 1 plus root 3. If we use the intersection symbol, that would imply that we need the values to satisfy both conditions. The union symbol means we can get anything that satisfies this condition, and then separately anything that satisfies this one, and we are happy to describe the entire set of solutions as anything which is in this class or in this one. So either of these two sets is fine. We know that there's no overlap between those, but that's not relevant when we're using this. This is effectively the OR, the inclusive OR that we use. And we should check at the end that our answers make sense. Remember, 1 plus root 3 is approximately 2.7. Minus 1 plus root 3 is going to be approximately 0.7. You can check those on the calculator, but see if they fit here. The 0.7 we've got is below root 2, and the 2.7 is above root 2. So these are consistent. My diagram's not the best, so it's not necessarily going to look like it's to scale, but the numbers at least are consistent with what I'm expecting, and I'm therefore happy with this result. There's one other thing you can do to check this. It's a little bit awkward on the calculator, but there is, I believe, an absolute value function. If we go to menu option number 9, so we're in table mode, we can use Shift and then the left button here to put absolute value signs around something. Then we can type in x squared minus 2. There's my first function. For my second function, I just want 2x. That's nice and straightforward. Now the table range straight away will give me a few values for positive numbers, and you might be able to just skim down and have a look at what's happening. So 1 and 2. Okay, as soon as we get to 3, we find that f of x overtakes g of x. And if you want to see more, you just keep pressing equals on your calculator. It'll give you a few more values. And you can see that in the long run, the quadratic is winning. We're interested in values close to the region that we've identified here. We want to test to see if numbers in this range satisfy the inequality and if numbers outside the range don't. So we might try a number like maybe 1.1 plus root 3. 1.1 plus root 3 is slightly above 1 plus root 3, and according to this, anything above 1 plus root 3 should be fair game. And it's coming out as 6 point something for the quadratic and 5 point something for the straight line. So it seems to work. And then I can try 0.9 plus root 3 instead. That's something just the wrong side of the inequality sign. And now the quadratic is below the straight line. So that's encouraging. You can do a similar thing for the other end, but we're not going to try that now.